What if I told you that we could get fresh, clean, drinking water, not from a river or a lake or a well, but by literally pulling it straight out of the air around us, even in a dry desert climate? It sounds like something out of science fiction, right? But it's a technology that's becoming very real, very fast. So, how on earth does it work? Let's break it down. First, let's just wrap our heads around the problem we're trying to solve. The numbers are just staggering. According to the World Health Organization and UNICEF, 1 out of every 3 people on Earth doesn't have access to safe drinking water. That's more than 2 billion people. This isn't some far-off problem, it's a full-blown crisis right now. But here's the incredible part. Floating right above our heads, in the atmosphere, there's this enormous, completely untapped reservoir of water. We're talking about 13,000 cubic kilometers of fresh water, just hanging out as vapor. I mean, that's a sustainable source that could, in theory, give water to everyone, everywhere. The big question has always been, how do we actually get to it?
So, here's what we're going to dive into. We'll start with the scale of the problem on our thirsty planet. Then, we'll look at how you can actually pull water from thin air using a brilliant new kind of sponge made from plants. We'll check out how it performs, and finally, we'll see where this all fits into the bigger race for clean water.
Okay, first up, the thirsty planet. With all our traditional water sources getting more and more stressed, getting clean water to everyone is one of the biggest challenges of our time. It's driving this huge need for new, innovative, and kind of decentralized solutions.
And that brings us to this new frontier, atmospheric water harvesting, or AWH for short. The whole idea is beautifully simple. Instead of drilling down for water, we just need to look up.
So how does this magic trick work? Well, the basic idea is pretty straightforward. You use a special material called a sorbent that just naturally loves to soak up water vapor from the air. Think of it like a high-tech sponge. Then you just need a way to squeeze that captured water out as pure liquid H2O. The real secret, of course, is in that sponge. So, if you're a scientist trying to build the perfect water-sucking sponge, what's on your wish list? Well, it needs to soak up a ton of water, obviously. It has to do it fast, and then release it easily on demand without falling apart after a few uses. But here's the kicker. The whole process has to be super energy efficient and made from sustainable stuff, because we don't want to just trade one environmental problem for another.
And that brings us to the hero of our story today. A team led by Gi-Hua Yu at the University of Texas at Austin has come up with a really remarkable new material that checks pretty much all of these boxes. And their big innovation doesn't start in some complex chemical plant. It starts with some of the most common materials on the entire planet.
You see, a lot of the early water-absorbing materials, these things called hydrogels, were made from petroleum-based plastics. And yeah, they worked, but they weren't exactly eco-friendly. So Yu's team went a completely different route. They turned to natural biomass. We're talking stuff like cellulose from plants, starch from corn, even chitin from the shells of crabs and shrimp. These materials aren't just sustainable, they're incredibly abundant and cheap.
So what exactly is a hydrogel? The simplest way to think about it is like a 3D net of tiny fibers. It's mostly just empty space, which makes it unbelievably porous. That porous structure lets it soak up a massive amount of water compared to its own weight. It's basically a high-tech, super absorbent sponge. So how did the team turn simple plant matter into a super sponge? This is where the real genius comes in. It was a clever 2-step upgrade. First, they added what you could call heat squeeze groups. These are special molecules that, when you warm them up just a little bit, they cause the whole gel to contract and literally wring itself out. Then, they added water magnet groups. These act like tiny little pillars that prop open the gel's internal structure, creating way more surface area to attract and hold on to even more water vapor. Okay, so that's the theory. Sounds pretty amazing, right? But the real question is, did it actually work? Well, the lab results are nothing short of stunning. I mean, just look at this comparison. Even in really dry air, we're talking only 30% humidity, a standard, off-the-shelf gel soaks up about half its own weight in water. But this new, engineered hydrogel, it soaks up 1.32 grams for every single gram of gel. That is more than double the performance. That 2-step upgrade was a total game changer. But remember, soaking up water is only half the battle. You have to be able to get it back out. And this is where those heat squeeze groups really shine. With just a little bit of gentle heat, up to 60 degrees Celsius, that's a temperature you can easily get with some low-grade waste heat or a simple solar panel. The gel releases 95% of all the water it captured. It's just unbelievably efficient. So what does this actually mean in the real world, outside the lab?
Well, in outdoor tests in Austin, Texas, with a system that was optimized to run fast cycles, the team was able to harvest an incredible 14.19 kilograms of water for every 1 kilogram of their gel, every single day. To put that in perspective, that's almost 4 gallons of pure water from just over 2 pounds of material. That is a truly remarkable yield.
Of course, there's one all-important question. Can you actually drink it? The team tested the water they collected, and they found that the concentration of any ions was way below the standards set by the World Health Organization for safe drinking water. So yep, the water is clean, it's pure, and it's ready to drink.
Now, this plant-based hydrogel is an amazing innovation for sure, but it's not the only horse in this race. The whole field of atmospheric water harvesting is just exploding right now with new ideas and new materials, all competing to be the most efficient and scalable solution out there.
Its main competitor is a different class of material called a metal organic framework, or a MOF. You can think of it like a classic tortoise and hare race. The biomass hydrogel, that's our tortoise, is made of sustainable stuff and holds a lot of water in one big go. The MOFs, they're the hares. They hold less water each time, but they are incredibly fast and they can cycle dozens of times a day, which could lead to a huge daily output. Both approaches have really compelling advantages.
But despite the challenges and the different technologies in the running, the leaders in this field are incredibly bullish about the future. Cody Friesen, who's a real pioneer in this industry, predicts that as this technology scales up, kind of like solar panels did, AWH is eventually going to become the cheapest way to deliver clean drinking water to any place on Earth. So we've arrived at this pretty amazing moment. The science is here. We have these materials that can literally pull clean, fresh drinking water right out of thin air, powered by nothing more than sustainable plants and a little bit of heat. The question really isn't can we do it anymore? The question now is, what's it going to take to bring this life-saving technology to the billions of people who need it most? That is the challenge, and the incredible opportunity that lies right in front of us.